Welcome back to Dave Does Math at Home. We're still talking about exponential functions, and we're about to get into the weird stuff. So far we've done addition and subtraction behind the function, multiplication in front of the function, and negative numbers in front of the function. The thing that all of those transformations have in common, the two things, is that the transformations are happening outside the function, so either in front of or behind it, not in the function where the 3 and the x connect, but outside of it, before or behind. The other thing they all have in common is they all produce vertical effects. Addition and subtraction on the outside is either going to shift you up or down. Multiplication on the outside is either going to stretch you if it's a whole number, or squish you if it's a fraction, or flip you upside down if it's a negative. But all of those are vertical effects. Shifting up, shifting down, stretching taller, getting shorter, flipping upside down. It's all vertical. So this is the video where we talk about the other kind of transformation, where the transformation happens on the inside of the function. So instead of messing with the 3 to the x while it's in parentheses and safe, we're going to mess with the x itself in the exponent. So we're going to move inside the function. The other weirdness that's going to happen with these transformations is they are all going to affect the function horizontally. And I will explain why in just a moment. Stay tuned. Let's do this example, y equals 3. I'm going to stick with 3. 3 is a good, solid example number. Let's go 3 to the, I'll say x minus 2. So this is different from the 3 to the x minus 2 on the back end. If you subtract 2 outside the function, we know what that does. Creates a vertical shift downward 2 units. That's pretty tame. This time the minus 2 is inside the exponent. It's affecting the x term directly. So we're going to make a table of values. We're going to start with x. This table of values is still going to use 3 columns because I want to have one sort of column jump for the function itself, and I want to have a separate column jump for the transformation. The big difference here is they're going to happen in a sort of a weird order. If you start with an x value, the first thing that happens to that x value is you subtract 2. Then the function happens. This base function with the 3 raised to that number, that happens second. That means as I fill in this function, whatever goes in this column are going to be the numbers that end up as exponents on top of 3. So these are the numbers that I want to be like my nice standard issue set of numbers that I use as exponents. So I'll fill in this column with my standard issue exponent numbers. Negative 2, negative 1, 0, 1, and 2. These are the things I've been using as exponents on top of 3 the whole time, and I don't want to stop. When I use them as exponents on top of 3, I'll get 1/9, 1/3, 1, 3, and 9, just like normal. That hasn't changed. Here's the weird part. I started with the x minus 2 column. So now if I want to get back to the x column to figure out what x originally was to create these values in the x minus 2 column, I have to move backwards and add 2. So if x minus 2 is negative 2, that means that x was originally 0. If x minus 2 is negative 1, x was originally 1. This one was originally 2. This was 3. This was 4. These are the numbers x has to start as, so that after you subtract 2, you end up with a standard set of negative 2 through 2. So these are the x values that I'm going to pair with these y values. Okay. As usual, I'm going to draw the base unedited standard issue function in blue. it's going to go through here, and then 3, and then 9, and 1/3, and 1/9. So the standard issue unedited base function looks like this. Still has its horizontal asymptote at 0, still has its intercept at 1. This is the base function, y equals 3 to the x. And now I'm going to use the transformed function. The transformed function hits this y equals 1 point 2 units to the right when x is 2. It hits this y equals 3 point 2 units to the right when x is 3. It gets to 9 when x is 4. Here's your 1/3. There's your 1/9. So there's that function. And the relationship to the base function is it went 2 to the right. Just moved over 2 units in this direction, which seems pretty counterintuitive. This transformation involves a negative number. We are subtracting from x. When we subtracted from the whole function on the outside, it went down, because subtraction intuitively should take you in the negative direction. And outside the function it does. Subtraction goes down, addition goes up. Inside the function, things work backwards, and it's because of this. This x minus 2 are the numbers we want to use, and to get the original x values, you have to undo this transformation to get what x should be. So we're adding 2 to these numbers to get the original x values, and that adding 2 to go backwards to the x values is what's pushing these x values to the right. So that's what's happening there. As a quick follow-up, we can talk about y equals 3 to the x plus 1. I'm not going to do a full table of values for this. You can if you like, and I would encourage you to in your own time. But I want to keep these videos moving along at a pretty quick pace. So I'm just going to tell you right away that this plus 1 on the inside is a shift to the left, in the same way that subtracting 2 pushed us 2 units to the right. Adding 1 is going to push us 1 unit left. So I'm just going to draw what that looks like. This is the standard, the base. Y equals 3 to the x. This is the y equals 3 to the x plus 1. It's just moved to the left 1 unit in all places. There's one other kind of transformation we need to talk about. And that is multiplying on the inside. So I want to do y equals 3 to the 2x. I want to do y equals 3 to the 1/2 x. And I want to do y equals 3 to the negative x. I think we can do all 3 of these in one big swoop. I'm going to start with this one. Once again, I'll need 3 columns. These are the numbers that I want to use. So this will be the standard issue, -2, -1, 0, 1, and 2. These are the numbers that are really easy to put as exponents on top of 3. So this would be 1/9, 1/3, 1, 2, and 9. But to go backwards from this collection of nice numbers into what the original x values need to be, I need to divide by 2. So these actual x values should be -1, -1/2, 0, 1/2, and 1. So our base graph is still, oh no, I want to do the base graph in blue. Yeah, okay, base graph still hits the y-axis there, 3, 9, 1/3, 1/9. There's the base graph. Transformed graph has the same intercept. So it's going to hit this graph right here. It's going to hit this point at 1/2 instead of 1, and it's going to hit this point at 1 instead of 2. It's going to hit this point at -1/2 instead of -1, and it'll hit this point at -1 instead of -2. So we have a function here that's thinner. Whatever this distance was got squished in half. Whatever this distance was, that got squished. This distance got squished. This distance got squished. This transformation makes things thinner. This is another squish. Trying to erase the green out this so I can make this one in green. If you want to make a table of values for this next one, I encourage you to. If you want to skip that part, and trust me, you can. If putting a 2 here makes it thinner, half as wide, putting a 1/2 here should make it twice as wide. So that'll put me at 3 out here, 9 out here. Same intercept. Making this point wider does nothing because its x value is 0. 1/3 is here, 1/9 is back here. So this one is wider. It's a stretch. Grab red for this last one. This one, interestingly, is the same as 3 to the -1 is 1/3 to the x. So whole numbers with negative exponents is the same as fractions with positive exponents, and that is going to be the flip. Whatever the x values were to get these values, we're just going to make them all negative. So you'll hit your 3 at -1, and your 9 at -2, and here you'll get your 1/3, and there your 1/9. This, hopefully that's showing up. Looks like the red is not doing great. This, I call this a flip, left to right. The book is going to call this one a horizontal reflection. So, quick recap. You can add, subtract, multiply, divide, make negative. Those are the 5 operations you can do. You can do them on the inside or the outside of the function. Addition and subtraction will shift the graph up, down, left, right. Multiplication and division will stretch or shrink, squish the graph. Vertical, horizontal, stretch, squish. Multiplying by -1 will flip it. You're either going to flip it upside down or left or right. And the golden rule of thumb is things that happen outside of the function create vertical effects in the direction you expect. Things that happen inside the function create horizontal effects in the opposite direction you would expect. That's it for this video. Enjoy the homework.